I'll try my best. So the first talk, I believe Jonathan Roth is going to be the speaker. So Jonathan, could you share your screen?
Yep. Can people see that?
Yes.
Can people see it now that I go full screen?
Yes.
Great.
So the first talk of this session will be bias in, bias out, evaluating the folk wisdom, and Jonathan Roth will be giving the talk.
Great. So thanks so much to the organizers. I'm excited to present this joint work with my awesome co-author, Ashish Ramachan, which is titled Bias In, Bias Out, Evaluating the Folk Wisdom. And so as has been discussed now at length in this conference, algorithms are being sort of employed in an increasing number of important domains to make decisions. And one of the big concerns about this is that if the humans generating the training data are discriminatory against certain groups, there's concern that the algorithmic decision rule will itself be discriminatory. And this is nicely captured in this phrase, bias in, bias out, which you may hear a lot. But the motivation for this paper is that statements about how bias in training data translate to the form of algorithmic decision rules, we think are often somewhat imprecise. So in particular, what does it mean exactly for humans to be biased in their decision making that generate the training data? And how does human bias then manifest itself into algorithmic decision rules? And in particular, if the humans are biased, is the resulting algorithmic decision rule necessarily itself biased? And so what we do in this paper is try to take an initial step towards formalizing some of these notions by sort of adapting a sort of classical taste-based model of discrimination in economics to use that as sort of a lens for how do human biases in training data affect algorithms that are trained on this data. And so to give you a sense of the key results in this paper, what we show in this paper is that things may be a bit more complicated than sort of the usual intuition that we have that bias in produces bias out. So we show in our model that while this bias in, bias out intuition holds for certain prediction exercises, human bias in training data need not necessarily produce discriminatory algorithms. And in fact, for what we think is an important class of prediction exercises, the opposite actually holds for a naively trained algorithm, meaning that the more biased is the human decision maker generating the training data, the more the resulting algorithmic decision rule is actually favorable to the discriminated against group. And this is a phenomenon that we call bias reversal. And we then in the paper try to sort of explore different different sort of modifications to the model that sort of try to highlight what is sort of the important features of the model that produce this bias reversal versus the usual bias in, bias out intuition. And one of the key factors that we highlight in this exercise is that it's very important the way that the human bias enters the training data set. And in particular, we draw a distinction between two ways the human bias may enter the training data set. The first being selection into training data, meaning which units are sort of contained in the training data, and the second being mismeasurement of the label. So what is the, sort of similar to in John's talk just now, what is the label that's being used for training versus the sort of objective label that we actually care about. So to give you a little bit more of a sense of our context, we are thinking about settings where there are so-called selective labels, meaning that we only observe outcomes to train the algorithm in cases where the human decision maker takes a particular action. So for example, in hiring settings, we may only observe a worker's performance if the worker is hired at a company. Likewise, in criminal justice context, we may only observe whether an individual commits a crime if a judge chooses to release that defendant on bail. And similar types of settings arise in medicine and finance. And so in the interest of time, I'm not going to have the chance to go through sort of the formal model, but let me try to give you some intuition for this sort of bias reversal result. So we're going to consider settings, as I mentioned, where training data is only generated if a potentially racially biased decision maker takes a particular action. So as an example, suppose job performance is only observed for a particular candidate if that candidate is hired. And then in our model, individuals in the training data are going to be selected by the human decision maker based on factors that some of which are observed by the data scientist and some of which aren't. So managers may hire based on sort of hard information that's passed along to the algorithm, but also based on, say, soft information from the interview that doesn't necessarily get recorded for the algorithm. And so based on this sort of selective data generation, the individuals who are in the training data set are not going to be sort of representative of the true population in terms of their soft information. In this example, they're generally going to sort of be positively selected on soft information that's correlated with higher productivity. But this type of selection actually goes in favor of the sort of disadvantaged group if the decision maker is biased. So in this context, if the manager is more racially biased, then in order to get hired and make your way into the training data, a minority applicant will have to be very good. And so there's actually a very positive selection on this soft information for the minority group. And as a result, the more biased is the hiring manager, the more an algorithmic decision rule trained on this selected data to predict their productivity would actually recommend hiring more minorities. So to try and dig in just a little bit on sort of why this is the case and what is different in this example from this sort of usual intuition. So here I have this table, and the intuition I've described so far is for the sort of first row in the table, where the prediction exercise is to predict the outcome of interest, which is assumed objectively measured, in our case, productivity, in a training sample that's selected based on the human decision maker's decision. And in this case, we get bias reversal, whereas by contrast, if we predicted, say, the human decision maker's decision S in the full sample, so if we just tried to automate the hiring decisions, then we would get the sort of the usual bias in, bias out phenomenon. And so what differs between these exercises is that in our first exercise, the outcome of interest is properly measured. We measure productivity, but the bias affects the sample used for training. Whereas in the second exercise and some others we consider in the paper, the sample is fixed, but the bias increases a wedge between what we sort of think of as the objective outcome productivity versus the outcome that's used for training. And you could, of course, imagine there being sort of cases where both of these phenomena are present. So let me just briefly talk about what we think are some implications of this paper, and then I'll wrap up. So first of all, what this paper does not imply, we definitely don't think this paper implies that concerns about algorithmic bias are not valid, but we do think that discussions about how human bias sort of manifests itself into algorithms should be a bit more nuanced, and in particular, attention should be paid to how the human bias influences the training data. Does it affect the labels, the selection, or both? Then one final thing is that if you sort of play these results in reverse, they also suggest that there's some settings where we sort of aren't currently necessarily thinking so much that algorithms may be biased, but that they may actually inherit bias. So for example, in settings where the humans are acting benevolently to try and, say, admit minority applicants to college, if you were then going to predict GPA among sort of admitted students, that could potentially lead the algorithm to be biased if the admissions committee, in its goal of sort of expanding access, admitted sort of applicants who may have lower grades. So I'm out of time, so I'll stop right there. But thanks so much for the opportunity to present this. And if you're interested, please check out the talk online, or the paper, which is on our websites and on archive.
Thanks a lot, Jonathan. So I didn't say it, but I'll say it now. For all the participants, you can ask questions in the Q&A or the chat window, or you can raise your hand. And I see a couple of questions, so I'll go ahead with those. So Galiona asks, whether you looked at dynamics over time, and does this type of bias reversal persist?
Yeah, so that's a great question. So the model in the paper is an entirely static one. So there's just one training data set, and then we train an algorithm on that to produce a rule. We think it's a really interesting question for future research. If you sort of start out with a biased training data set and you then use your algorithm to sort of select new candidates over time, and then you keep on adjusting based on sort of the new data that that gets observed, what this thing sort of converges to. It's not a question that we have answers for now, but something we think is interesting.
Okay, and now this is going to be a challenging question to read out, but I'll try. So Aloni Cohen asks whether by bias reversal, he says, you seem to mean that the expectation of, I'm going to read this as the expectation of y conditioned on x and s equals 1. Can you see the question in the chat window, Jonathan?
I can see the question,
easier.
Yeah.
Okay, okay. So Aloni asks, isn't the goal to learn the expectation or the probability that y equals 1 conditioned on x without conditioned on x without conditioning on s? So you can read the question and maybe answer.
Yeah, so we're thinking about settings where sort of the labels for training, so the Ys only get generated conditional on the human decision maker taking a particular action. So for instance, if we're thinking of Amazon making a hiring decision and they want to predict productivity, say, they have performance reviews for the candidates that they hired, but it's very hard for them to get performance reviews for the candidates that they didn't hire. So I think in that context, that's why it's natural for us to sort of think about the expectation conditional on S being equal to 1, because that's when the labels are generated. So I hope that answers the question.
Okay. So thanks a lot again for your talk and the answers. And we should move on to the next talk, which will be given by Sumega. So Sumega, if you could unmute and share your screen. Great.
Okay.
So the next talk will be on the role of randomness and noise in strategic classification by Mark Braverman and Sumega Garg, and Sumega will give the talk.
Thanks, Guy. And I want to thank all the organizers for bringing this workshop together, and thank you all for tuning in. So I'll start. The study of strategic classification was motivated by the following observation, that knowing information about the classifier, individuals might manipulate their attributes to get a favorable outcome. For example, if a student knows that a university heavily weighs SAT score in their admission process, then she will be motivated to achieve a higher SAT score either through test preparation or multiple tries. Such efforts by the student might not change their probability of success in a university, but are enough to fool admissions process. So the question is, how do we do meaningful machine learning amidst such manipulated data? So we start with the formalized setting for strategic classification defined by Hart et al. In 2016, where X is the feature set and classification is part of a game where a jury publishes a classifier first, and we represent this classifier with F. And then seeing this classifier F, in response, individuals manipulate their features to get a favorable outcome, but while incurring certain costs. And we denote this cost function by C, where C x comma x prime denotes the cost of manipulating from feature X to X prime. We assume that such manipulations don't change their inherent qualifications, and we represent the true classifier on feature X by H. And knowing the cost function and the classifier, individuals manipulate their features to delta X, which will be defined on the next page. This kind of game is studied using Stackelberg equilibrium, and F goes first and publishes, and F is published, and then in response, an individual manipulates its features to delta X, where an individual manipulates its feature as long as the advantage gained in classification, that is Fy minus Fx, is greater than the cost of manipulation, which is Cx, y. And in the end, the payoff to the jury is the probability that this classification with respect to delta x, which is f of delta x, is equal to the true classification, which is h of x. Because of this strategic manipulated data, it is possible that all f's at Stackelberg equilibrium might incur a payoff loss. And this payoff is less than 1. And in this work, we study addition of randomness and noise to the system and how this addition can help retrieve some of the loss in the payoff. It is easy to see that randomness and noise doesn't improve jury's accuracy in case of no strategic manipulation because we are losing information. But there are many examples in game theory where loss of information helps equilibrium outcomes, and we achieve similar results. In this work, we have two modes of adding randomness to the system. The first is that we allow the jury to publish a randomized classifier, F, where Fx is the probability of being classified as 1. And in the second case, we add noise to the features. Here, in this setting, each individual has a private signal Y associated with them, which identify their qualifications, and the features are noisy representations of this private signal Y. The jury bases their classification on the features, whereas every individual can manipulate their private signal but have no control over the noise that is added to the signal. What we show is the following. We show through examples that compared to deterministic classifier, in which a classifier associates with a deterministic classifier is one which associates with each feature a value 0 or 1. But we show that through examples that compared to deterministic classifier, randomized classification and addition of noise to features can lead to better equilibrium outcomes. That is better accuracy and fairness, even sometimes improving both at the same time. We also characterize most efficient randomized classifiers for simple cost functions and one-dimensional feature set. We argue about the advantage of using the mode of adding noise to the features over randomized classifier because of some kind of instability in the system caused by the latter. We don't have time to go into the results, but please visit the 20-minute talk on the program webpage for details. So in the next minute, I will give a simple example to show how randomized classification can benefit accuracy in strategic classification setting. So in this example, we have two features. We have a set of two features, A and B. And we assume that all the individuals at feature A are not qualified and all the individuals with feature B are qualified. And the cost of manipulating the feature from feature A to B is 0.6. As this cost of manipulation is less than 1, then if we classify individuals with feature B with 1 and classify individuals with feature A as 0, then individuals A would manipulate their features to B, and this will lead to an accuracy of 0.5 at the Stackelberg equilibrium. And in any other case, we will a deterministic classifier will classify them equally, either classifying them both with 0 or classifying them both with 1. So that means that any deterministic classifier cannot distinguish between A and B, and hence accuracy at Stackelberg equilibrium is at most 0.5 for any deterministic classifier. But if we classify all individuals with feature A with 1 with probability 0.5 and classify all individuals at feature B with probability 1 as 1, then the individuals at A don't have incentive to manipulate their features because the difference in the probabilities of classification is equal to 0.5, which is the advantage gained in manipulating the feature from A to B, and this advantage 0.5 is less than the cost of manipulation, which is 0.6, and the accuracy of F is 0.75 at the Stackelberg equilibrium. So on a high level, what the jury did was the jury selected some unqualified individuals with some probability so as to de-incentivize them to manipulate their features and hence achieving a higher accuracy at the Stackelberg equilibrium. Thanks.
Thanks, Sumega. So we have a question from Yonadav Shavit, and he asks, do the results about feature randomization also require classifier randomization, or do each of them help independently?
Yeah, each of them help independently.
Would you like to take the opportunity to say another word about your point about instability of randomizing the output?
Yeah. So let's look at the classifier that we achieved, randomized classifier that we achieved in this in the last example. What it did was it selected some unqualified individuals with some probability. So the most efficient randomized classifier actually looks like this, that it selects every individual with some probability, so as to de-incentivize them to move. And then now, if the classifier knows that no one has manipulated their features and are revealing their features, then it has an opportunity to actually use HX over the classifier H over these features, rather than using F, which is a randomized classifier. And we can formalize this notion of instability and say that in every setting, when a randomized classifier achieves better accuracy than any deterministic classifier at Stackelberg equilibrium, there's an opportunity for the jury to create instability in the system by changing their classifier.
Thanks. And I see one last question, and then we'll go to the next talk. Any thought from CL, any thought about how the introduction of noise might be perceived as unfair in itself?
Yeah, it's a good question. I don't think I have an answer to this. Like, okay, so yeah, I don't know.
Okay, thanks a lot for the interesting talk, Sumega. And if you could mute, and the next talk will be given by Sergey Mikhalishev. So Sergey, if you could share your screen and unmute your mic.
Okay, hello everyone.
Okay,
so can you hear me? And can you see slides?
Yes.
Okay,
yes,
great.
And I'll just say in a word that the next talk will be attentional role of quota implementation by Sergey Mikhalishev and Andrei Medvinko, and Sergey will give the talk. Go ahead.
Okay, so let me just check something. Sorry. Okay, anyway. So let's start. Okay, so I'm a PhD student in economics. So it's going to be a little bit different, but I hope it's going to be understandable also for computer science crowd. Okay, so it's motivated by the fact that when a HR manager sees a CV in first time, then he spends less than 10 seconds before he decides whether he wants to put the CV into the no pile or whether he wants to read it further. So this evidence tells us like two facts. So one, there's like a lot of information that actually not used in the choice decision. And the second one, the decision maker actually decides not just the action, but also decides what information he's going to acquire. So, and that brings us to the example. So let me use it. So we have an agent who decides whether he wants to choose a risky option or safe option. And safe option is also going to be 0.5, and risky option can be good, and then it's 1, or it can be bad, and then it's 0. And the agent can flexibly acquire costly information about the realization of the risky option. Okay. So the solution to this problem is going to be the following. So on this picture, we see the amount of information that the agent is going to acquire. And on the horizontal axis, we see the probability that the risky option is actually bad. Okay, so we see that if the probability of risky option being bad is really high or it's really low, then the agent decides not to acquire any information at all. Okay, so and the question that we're asking here in our paper is that, okay, so what's going to happen with the behavioral of the rational and attentive agent if we introduce quotas? And by quotas, I mean that, okay, so imagine you need to make this choice 100 times between risky and safe options, and I tell you, okay, in half of these attempts, you need to choose risky option. And then we ask the following question that, okay, if we know how the agent is going to behave, what we can achieve with quarters. Okay, so here's the answer for the first question. So it's the same graph. So it's amount of information that the agent is going to acquire. So red lines for different quarters and green line again for the unconstrained problem. And we see that it doesn't matter what the probability of risky options being bad or good. Under quarters, agent always going to acquire information. Okay, and then this result brings us that to answer to the question what we can achieve with quarters. So we can achieve quite a lot. So firstly, we can improve the quality of the choice. So if we can force the agent to acquire more information, then we can force the agent to make better choice in terms of quality of the choice. Yes, and then we can improve fairness. So by fairness, I mean here just that the similar options should be chosen with equal probability. And then on this graph, we have this expected value of the choice, quality of the choice. On the vertical axis, on the horizontal, we have again the probability that the risk option is bad. So green line for a constraint case, the dashed line for the value maximizing quarter. So if we want to maximize quality, so we can achieve it, not always. So on the corner, we will not be able to do it. But more interesting that, okay, so with quarter, we can make our choice fair. And at the same time, for a wide range of parameters here in the middle, we will not going to lose anything in terms of quality. So it seems like pretty amazing result. Okay, and let me just sum up. Okay, so if we introduce quarters and there's rational attentive agent, so he always going to acquire some information, and then we can achieve some goals if we introduce quarters, such as improve quality, reduce attentional discrimination, and correct for inaccurate statistical discrimination. Okay, so I didn't mention it, but basically, if the agent has wrong prior, then using quarters we can correct. In this case, we not like correct for this bias, improve quality, but we're also going to improve actually the agent's utility. And I just need to mention that it based on the assumption that the social planner knows a lot about the distributional parameters. So for example, if we relax the assumption that the social planner knows the value of, for example, of safe option, then we shouldn't introduce any quarter because we will not be able to achieve any of the mentioned goals. Okay, so it's all what I wanted to say. So thank you for your attention. And I refer to talk and to the paper that have more generalized results. Okay, so thank you very much for attention.
Thank you, Sergey. So please feel free to post questions in the Q&A. Since I don't see anything posted in there right now, I get to ask my own question, which is, so it seems that you're using the quotas to motivate a decision maker to seek out more information. And we know that it can sometimes be the case that, there are information disparities about different populations. This might motivate the decision maker, bias a decision maker towards populations where information is more readily available. Have you thought about that, or do you have anything to say about that?
So, okay, so your question about that some information about certain categories could be more costly than information about another category, or?
Yeah. So, for certain populations, information might be more readily available or easier to seek out than for other populations. Okay, so yeah, so here's the assumption that it's equally costly. Yes. So I cannot answer what's going to happen in this case. Yes. Okay, so food for thought. Yeah, thank you. Okay, great. So thank you, Sergey. And the next talk is going to be by Roy Dong. Roy, if you could share your screen and unmute.
Let me see. I'm going to have to ask if it's working in a sec.
It seems to be working. Great. So the next talk will be Learning Under Surveillance, Protecting Consumers Against Personalized Pricing Algorithms. And the talk will be by Roy Dong, work with Eric Mealing and Cedric Langford.
Hi, so it's an absolute pleasure to be speaking here, an absolute honor, and I just want to take time to thank the committee. This is really one of the most well-executed online conferences I've attended, and there are a lot of great conversations I had throughout. My name is Roy Dong. I'm a research assistant professor at Illinois, and today I'm going to be talking about learning under surveillance. And primarily, the sort of setting that I study a lot is data markets. So, from the consumer side, you've probably heard this referred to as surveillance capitalism. We're constantly generating this sort of data exhaust as we move day to day, and companies are monetizing that and using that to sort of set prices against us. And, there's a sort of underpinning anxiety about surveillance capitalism. And I really like to start this talk by contrasting this, because this is the consumer perspective, contrasting it with the company's perspective, where the term I view as analogous is the term digital transformation. And this is a screenshot from Bain & Company, one of the big consulting companies. And, from a company perspective, there's this fundamental anxiety about being left behind in the age of data. So on one hand, you have consumers anxious about how companies are using data. On the other hand, you have companies that are super anxious that they'll get left behind, and that, right now we're just in a business ecosystem where companies that don't use data will not be able to survive. So we have this anxiety from both sides, kind of just pushing and pulling on how data is used. So this is just sort of the context of the type of problem I'm interested in. For the purposes of this talk, I'm going to focus on just personalized pricing algorithms and, just a quick summary of what they are. They just are algorithms that use feature vectors of individuals to set prices customized for each person based on the information available to the company. And in particular, we're going to study these algorithms sort of that track a person across time. So a person has to learn under surveillance. So just to sort of contextualize the sort of stance this talk is taking, something that I'm not going to address at all, and I don't intend to take a stance on, is whether or not personalized pricing algorithms are beneficial to society. So I think on one hand, there's a lot of market matching benefits of it, that you kind of get this mutually beneficial trade happening that wouldn't have happened otherwise without personalized pricing. But I think if you think about the talks in this conference and use your imagination, you can think of ways that personalized pricing algorithms may be harmful or unfair. But I'm not going to discuss whether or not that's, the fairness accuracy trade-off or anything like that. Mainly the reason for this work is that from our perspective, it seems that most existing work focuses on the seller's perspective. So given the available data, how do we, taking the perspective of the seller, set prices to maximize revenue, to extract the most willingness to pay from the consumer, and so on. So what we started trying to do with this work, which is, right now it's currently a working paper, we're really interested in looking at algorithms from the consumer's perspective. So instead, the problem statement is, given the personalized pricing algorithm, how do we, now the consumer, make our purchasing decisions? So I'll just quickly go through the problem setup. The results are in the paper, and I discuss a little bit more of the intuitions in the YouTube video talk. The goal of this 5-minute recap is to just give an overview of sort of how we frame the problem. So in our problem setup, the consumer is considering the purchase of a single indivisible good. It takes place in discrete time with a finite horizon. And at each time step, the consumer learns more about her valuation while simultaneously revealing information to a seller. So at the beginning of the game, the seller credibly pre-commits to pricing strategies, PT, where each PT is a random variable. So you should think of each of these as contingency plans. Given the information available to the seller at time T, what is the price they're going to set? So PT, the realized value of PT is the actual announced price, but in advance it's announced as a contingency plan. And as time proceeds, the seller learns more and more about the consumer and targets prices at the consumer's willingness to pay. From the consumer's perspective, her available information at each time step is modeled by the sigma algebra FFT, and we assume that the sort of sequence of information states form this filtration. Since the seller announces the realized values of the prices at each time step, we assume that PT is going to be FT measurable. And just as an example, if the consumer observes a random variable YT at time T, then we can think of the canonical filtration generated by those random variables. So that's sort of the modeling framework we put it in. For more details, I can refer to the paper, but the basic idea is that as time proceeds, the consumer learns more and more about her own valuation of the good, and we assume her utility function is risk averse. So everything else equal, her payoff is going to be higher when she has less uncertainty about her own valuation. So at each time step, the consumer has to choose one of three actions. She can either purchase the good immediately, receive some payoff pi of t, and the game will end. She can reject the good immediately, and receive 0 payoff and the game ends, or she can continue learning and the game will just proceed to the next time step. So if you kind of agree with all these sort of modeling assumptions we put in, some of which are overly strong and we hope to relax in the future, we can reframe the problem as an optimal stopping time problem. And that can be solved using the Snell envelope and leveraging a lot of tools from stochastic and computational finance for the pricing of American options. Again, details of that are in the paper, but I just kind of want to point to these figures real quick as sort of an example. So on the left, you can see this green line represents the consumer's valuation, where the bars kind of represent her uncertainty. The blue line represents the seller's estimate of the consumer's valuation and his uncertainty kind of decreasing. And the red dotted line represents sort of the offered price that the seller will make given his estimate. And if you just had a consumer that purchased as soon as they had positive payoff, they would purchase in this example at time 13 and receive a kind of small payoff. Whereas if we use an optimal stopping time approach, they'll actually use a little bit of patience and wait and get a much higher payoff. And on the right, we can just see that sort of, although we don't have improved payoff in every realization, which wouldn't be possible, we do have an improvement on average. So this is just a histogram of the change in payoff, and the red line represents how the mean has shifted. So again, all more details of that are in the talk and paper. And just as a quick summary, so the goal of this work was to look at algorithms for the consumer to maximize their utility when learning under surveillance. So continuing to get data themselves while that learning process is under observation by an observer, in this case, the company. And we framed the problem as an optimal stopping time problem, and we're able to provide computational methods drawing from the state of the art in computational finance. And we're really hoping that this kind of sparks some conversation and sets the stage for interesting future directions that take the viewpoint of the consumer. I'm happy to field any questions now, or reach out to me via email. And thank you so much for your attention. And again, thanks to the organizers for a wonderful, really enjoyable conference.
Thanks, Roy. So everyone can post questions in the Q&A, and I'll just ask, for me, went a little bit quickly, so I'll ask a clarification question, which is, what's the information all parties see as we're going, from one time period to the next?
So yeah, that's a really good question. And right now in the working paper stage, we'd like to, we're in a stage where we want to advance that further. Right now, because the prices are pre-announced random variables, we don't have any sense of signaling. So really, the seller just kind of learns information across time and it sets the prices accordingly. We view that as just exogenously fixed, so we don't model that. And then the consumer usually learns more information just by some observations of random variables related to our own valuation.
So sorry, let me just clarify. What are the random variables related to the user's valuations?
Right. So sorry. Yeah. Sorry, that was a bad answer. The framework is relatively general, and we have an example in the paper where she iteratively receives less and less noisy observations of her true underlying valuation. Yeah. Sorry, that was a roundabout answer to the first time. Yeah.
Sure. Thank you. So we have a question from Ivani Radia Dixit. Did you explore how the seller might adapt in this game, given the knowledge of the consumer's strategy?
That's a really good question, and we're hoping to address that in future work. Right now, what we have calculated is, given the pricing strategies of the seller, what is the best response of the consumer? And what we're really looking to solve in the next step is actually the Stackelberg formulation. So yeah, exactly. Still supposing that the seller has the option to act first, but optimizing subject to the consumer using the best response that we kind of outlined in this paper.
Great, thanks. And then I'll ask a question that's sort of out of scope, but I'll ask it anyway. Since you've thought about personalized pricing, do you think this is something that might actually lead to wider spread adoption of privacy protective tools by consumers?
Yeah, we really hope so. And to be absolutely frank, right now I think it's in the early stages where it's not quite deployable because of the assumptions we need in terms of the random variables and their form. But we're hoping that as we soften the assumptions, it can become an algorithm that could be potentially something like a web browser plugin or something that would easily help with these sorts of settings. Yeah.
Great, thanks, Roy. And I think that brings us to the end of the session and the end of the contributed works. So
right.
I'll hand things back to Aaron.
Yeah, so that's a wrap. That's the end of FORC 2020, the inaugural FORC. And let me just close things out by thanking everyone involved. You know, this went, I think, extremely well, especially given the circumstances. The steering committee, the program committee, the authors, the attendees, you know, everything just went swimmingly. And there's more. If you haven't watched them yet, all of the talks you saw over the course of this online event have corresponding longer form 20-minute talks on YouTube, and you can find them by going to the responsiblecomputing.org website and clicking through links that are next to the talk titles on the program. And within the next couple of days, we're gonna try to get all of the live sessions, including both the keynote talks and the contributed sessions, available online as well. They've all been recorded. And so I don't know if Cynthia and Omer want to say anything. But,
yeah, so mainly to thank you, Aaron, for marvelous job, really wonderful. You had to do a lot of firsts here, not only the first fork, but the first one in these battle conditions. And perhaps to ask everybody to start thinking about their best work for FORC 2021 that will be at Harvard roughly a year from now. Cynthia?
You said it all perfectly. Let me particularly call out the CMSA, Harvard Center for Mathematical Sciences and Applications, for, I think, agreeing within about a minute and a half of when I asked if they would sponsor us, and also flexibly sponsoring us for next year, and for providing all of the support for making the online work. In particular, Ryan Maloney was tremendously helpful in making everything run smoothly and educating us on how to do this online. And we expect that next year will be in the second week of June, and we're nailing down the date. Okay, thank you.
next year in person.
Next year in
Hopefully.
person. Okay, bye-bye.
Bye.